Welcome to a place where the night wraps around you like a soft blanket, where the quiet hum of evening settles into your bones, where we can pause together and look upward into something so immense that our minds can barely hold its edges. Tonight, we will travel through a paradox that sits at the heart of modern astronomy, a puzzle that reveals just how little we truly know about the universe we inhabit. Wherever you are right now, whether you are nestled into bed with pillows arranged just so, whether you are sitting in a favorite chair with a cup of something warm beside you, whether you are listening in the dark with only the glow of a screen to keep you company, I want you to take a breath and settle in. Let the day's urgency fade. Let the tension in your shoulders drop. Let your mind drift upward, past the ceiling, past the atmosphere, past the moon and planets, out into the black ocean of space, where we will spend the next few hours together. There is no hurry. There is no test at the end. There is only the gentle unfolding of a story about light and distance, and the profound mystery of what remains hidden from our view. Before we begin this voyage, if you find value in these explorations, a gentle click on the like button or a subscription to the channel helps us continue creating these calm journeys through cosmic knowledge. Your support allows these conversations to continue, these quiet investigations into the nature of everything. And now, let us drift together into the great unseen, the illusion of completeness. When you step outside on a clear night, far from the glow of cities, far from the artificial suns we have created to push back the darkness, you can see perhaps 3,000 stars if you are in the northern hemisphere, and a similar number if you are in the south. Under absolutely perfect conditions, with exceptional eyesight and the clearest skies imaginable, the human eye can perceive roughly 9,000 individual stars across the entire celestial sphere. 9,000 points of light, each one a sun, each one perhaps surrounded by worlds of its own. It feels like abundance. It feels like the sky is filled with stars, countless and infinite. But our galaxy, the Milky Way, that great spiral of stars and gas and dust that is our cosmic home, contains somewhere between 100 billion and 400 billion stars. Let us consider this carefully. We can see 9,000 stars with our naked eyes. Our galaxy contains hundreds of billions. The fraction is so small, it almost disappears into insignificance. You are seeing roughly 2/100ths of 1,000th of 1% of the stars in our galaxy alone. It is as though you stood in a vast library containing millions of books, and you could read only a single page from a single volume. And from that page, you were asked to understand the entire collection. Now let us extend this thought further, because the Milky Way is only one galaxy among an almost unimaginable multitude. Current astronomical research suggests that the observable universe contains approximately 2 trillion galaxies. Each of those galaxies holds anywhere from a few million to several trillion stars. When we multiply these numbers, when we calculate the total stellar population of the observable universe, we arrive at an estimate of around 200 billion trillion stars. That number is so large, it loses meaning in human terms. It is a quantity that exists only as an abstraction, a string of digits that our minds cannot truly grasp in any visceral way. And of those 200 billion trillion stars, we can see 9,000 with our unaided eyes. We are not looking at the universe. We are glimpsing the tiniest fragment of a fragment of a fragment. A view so limited that calling it incomplete feels like a profound understatement. The census we have not taken. But let us set aside stars for a moment and focus on galaxies. Because galaxies are the fundamental structures of the cosmos, the cities of stars, the basic architectural units from which the universe is constructed. 2 trillion galaxies fill the observable universe, scattered across distances so vast that light from the farthest ones has been traveling toward us for more than 13 billion years. 2 trillion is the number we have arrived at through careful observation and mathematical modeling, through surveys that have scanned portions of the sky and extrapolations that extend those observations to the regions we have not yet examined. But here is the remarkable thing, the fact that should make you pause and consider carefully. Of those 2 trillion galaxies, we have observed in any meaningful detail only a small fraction. The most comprehensive surveys completed as of this moment in time have cataloged and studied somewhere between 10 million and 50 million galaxies. Let us be generous and call it 50 million. The arithmetic is straightforward. 50 million out of 2 trillion represents approximately 25 thousandths of 1%. Put another way, for every galaxy that astronomers have examined, there are roughly 40,000 galaxies that remain unobserved, unstudied, unexamined. If the universe were a great encyclopedia containing 2 trillion entries, we have read about 25 of them, and from those 25 entries, we are attempting to understand the totality of cosmic knowledge. This is not because astronomers are lazy or incurious. It is not because the telescopes are insufficient or the methods inadequate. It is because the task is so enormous, so overwhelming in its scope, that even with centuries of effort and the most powerful instruments humanity has ever constructed, we have barely begun to scratch the surface. The geography of sky. To understand why so much remains unseen, we must consider the nature of astronomical observation itself, the practical realities that constrain what we can study. The sky above us is not a small place. When we speak of the celestial sphere, the imaginary dome upon which stars and galaxies appear to be fixed, we are describing a surface that covers approximately 41,000 square degrees. This is the totality of the sky, the complete vista that surrounds Earth in all directions. Now consider how telescopes work. The most powerful instruments, the ones capable of detecting faint and distant galaxies, do not survey the entire sky at once. They look at small patches, tiny windows, narrow fields of view through which they gather light for extended periods. The famous Hubble Ultra Deep Field, one of the most profound images ever captured, shows approximately 10,000 galaxies in a region covering about 1/13 millionth of the entire celestial sphere. Imagine the sky as the size of North America. The Hubble Ultra Deep Field would be about the size of a tennis court. And to capture that single image, Hubble stared at that one patch of sky for hundreds of hours, accumulating exposure time across hundreds of individual orbits around Earth. This is the fundamental constraint. To see faint objects, to detect galaxies at enormous distances, you must stare at one place for a very long time. But the sky is vast. There are millions of such patches, each requiring hundreds of hours of observation to see deeply. There are not enough telescopes, not enough hours in the year, not enough years in a human lifetime, or even in the lifetime of our current technological civilization, to observe them all. We must make choices. We must select which regions of sky to study and which to leave dark. Every choice means something remains unseen. The difference between seeing and knowing. There is another subtlety here, another layer to this puzzle of the unseen universe. Not all observations are created equal. There is a profound difference between detecting a galaxy and truly understanding it. Detection might mean that your telescope has captured enough photons to confirm that something exists at a particular location in the sky. You see a faint smudge, a small concentration of light against the background darkness. You can measure approximately how bright it appears, and perhaps you can determine its color, whether it appears more blue or more red. This is valuable information, but it is minimal. It tells you that a galaxy exists, and it gives you rough clues about its distance and properties. But it does not tell you much more. To truly understand a galaxy, to know its distance precisely, to determine what kinds of stars it contains, to measure how fast it is moving, to understand its chemical composition and its history, you need something more. You need spectroscopy. Spectroscopy means splitting the galaxy's light into its component wavelengths, creating a spectrum, a rainbow of colors that carries encoded within it a wealth of information. Different elements absorb and emit light at specific wavelengths, creating patterns of dark and bright lines in the spectrum. By studying these patterns, astronomers can determine what a galaxy is made of, how fast it is moving, how old its stars are, whether new stars are forming, and countless other details. But spectroscopy takes time, far more time than simple imaging. You must gather enough light to create a spectrum with sufficient detail to analyze, and for faint, distant galaxies, this can require hours or even days of observation. The Sloan Digital Sky Survey, one of the most ambitious mapping projects ever undertaken, obtained spectra for approximately 2 million galaxies over many years of work. 2 million sounds impressive until you remember that there are 2 trillion galaxies in total. That means roughly 0.1% of all galaxies have been studied spectroscopically. The other 99.9% remain as little more than faint dots in images, detected but not understood, seen but not known. The spectrum of invisibility, think of it this way, and let this metaphor settle into your mind as we drift through these ideas together. Imagine you are trying to understand all the cities on Earth, every human settlement, every place where people gather and build and live. Photometric detection, simple imaging, is like flying over a city at night in an airplane. You look down and see lights. You can tell that a city exists. You can estimate roughly how large it is based on how much area the lights cover. You might be able to guess whether it is a large city or a small town. But you do not know what the buildings look like. You do not know what languages the people speak. You do not know what kind of economy drives the place. What cultural traditions shape daily life. What history has unfolded there over centuries. You know only that lights exist in that location. Spectroscopy is landing. It is walking through the streets, talking to people, studying the architecture, reading the signs, learning the history, understanding the place in depth. We have done the equivalent of detailed ground visits to about 2 million cities out of 2 trillion. The rest are just lights seen from an airplane window. This is the unseen universe in one of its forms. Not galaxies that are completely invisible, but galaxies that are seen only in the most superficial way, detected but not examined, present but not understood. Their light has reached us, has been recorded by our instruments, but we have not yet devoted the resources necessary to truly study them. The dimming of distance. Distance creates its own form of invisibility. The universe is not static. It is expanding, has been expanding since the Big Bang, and this expansion affects every photon of light that travels through space. When light leaves a distant galaxy and begins its journey toward Earth, the space through which it travels is expanding. This expansion stretches the light, increasing its wavelength, shifting it toward the red end of the spectrum. We call this redshift. The farther away a galaxy is, the faster it is receding due to cosmic expansion, and the more its light is redshifted by the time it reaches us. A galaxy that is very far away might emit most of its light in the ultraviolet part of the spectrum. But by the time that light reaches Earth, it has been stretched into the infrared. Our eyes cannot see infrared light. optical telescopes that observe visible light cannot detect it. To see these distant galaxies, we need infrared telescopes, instruments specifically designed to capture light at longer wavelengths. The James Webb Space Telescope, launched at the end of 2021, is such an instrument. Webb's mirrors and detectors are optimized for infrared observations, allowing it to see galaxies that are invisible to Hubble and to all optical telescopes. In its first few years of operation, Webb has revealed galaxies from the very early universe, galaxies whose light has been traveling for more than 13 billion years, galaxies that formed when the cosmos was only a few 100 million years old. But even Webb has limits. There are galaxies so distant, so deeply redshifted, that their light falls beyond even Webb's infrared range. And there are galaxies so faint that even with long exposures, Webb cannot gather enough photons to detect them. These galaxies are not gone. They exist. They are shining right now, wherever they are in space. But their light, dimmed by distance, stretched by expansion, scattered by the vast emptiness between here and there, is too faint for us to capture. They are part of the unseen universe, beyond the reach of current technology, waiting for future instruments that might be sensitive enough to bring them into view. The veil of dust. Our own galaxy creates another barrier to observation, a cosmic fog that blocks our view of distant realms. The Milky Way is a disk of stars and gas and dust, roughly 100,000 light-years across and only about 1,000 light-years thick in most places. We are located within this disk, about 26,000 light-years from the center. When we look toward the galactic center, or when we look along the plane of the disk in any direction, we are looking through enormous quantities of dust. This dust is made of tiny solid particles, smaller than the width of a human hair, composed of carbon and silicates and ices. These particles are scattered throughout the interstellar medium, the space between stars, and they affect light in two ways. First, they absorb light, particularly blue and ultraviolet wavelengths. Second, they scatter light, sending photons off in random directions. The combined effect is that dust makes distant objects appear dimmer and redder than they actually are. When the dust is thick enough, it blocks our view entirely. There is a band around the sky, roughly 20 degrees wide, centered on the plane of the Milky Way, where we cannot see distant galaxies at visible wavelengths. Astronomers call this the zone of avoidance. It is not a poetic name. It is a practical description. We avoid observing in this region because optical observations are compromised by dust. The zone of avoidance covers about 10% of the entire sky. Within this region are an estimated 100 million to several hundred million galaxies that we cannot observe at visible wavelengths. Some can be detected using infrared or radio telescopes, which can penetrate dust more effectively. But these observations are more difficult and less detailed than optical surveys. Most of the galaxies in the zone of avoidance remain poorly studied. They are hidden behind the veil of our own galaxy's dust, invisible not because they are far away, but because we are looking at them through a cosmic smokescreen. The architecture of time. There is another dimension to the unseen universe that is more subtle, more philosophical, but equally important. When we observe distant galaxies, we are not seeing them as they are now. We are seeing them as they were in the past, when the light we are receiving left them and began its journey across space. Light travels at a finite speed, roughly 300,000 kilometers per second. And this means that looking out into space is also looking back in time. A galaxy 1 billion light-years away appears to us as it was 1 billion years ago. A galaxy 10 billion light-years away appears as it was 10 billion years ago, when the universe was much younger than it is today. This creates a strange situation. When astronomers create maps of the universe, showing where galaxies are located, they are not creating maps of the universe as it exists now. They are creating maps that show different galaxies at different times. A nearby galaxy appears in its recent state. A distant galaxy appears in its ancient state. It is like making a photograph of your family where each person's image is from a different decade. Your image is from this year. Your sibling's image is from 5 years ago. Your parents' images are from 20 years ago. Your grandparents' images are from 50 years ago. The photograph does not show your family as it exists now. It shows a composite across time. Our maps of the cosmos are similar. They are composites showing the universe at many different epochs, all superimposed onto a single view. The true present state of distant galaxies is invisible to us. We cannot see what those galaxies look like right now because the light showing their current state will not reach Earth for billions of years. In a very real sense, the present state of most of the universe is fundamentally inaccessible to us. We can only observe the past, layer upon layer of history, stretching back toward the beginning of everything. The present remains unseen, hidden not by distance or dust or faintness, but by the simple fact that information takes time to propagate. And the universe is so vast that most of the information about what is happening now will not reach us for eons. The smallest galaxies. Let us turn our attention now to specific populations of galaxies that make up large portions of the unseen universe. We will begin with the smallest galaxies, the dwarf galaxies that constitute the majority of galactic populations, but which are exceedingly difficult to detect at large distances. A dwarf galaxy might contain only a few million to a few billion stars, compared to the Milky Way's 100 billion or more. This makes them intrinsically faint. Even though they are numerous, far more common than large galaxies, they are much harder to see. In our local neighborhood, within a few million light-years of the Milky Way, we have identified approximately 80 galaxies that are members of what we call the local group. Most of these are dwarf galaxies. The Milky Way and Andromeda are the two dominant members, large spiral galaxies with hundreds of billions of stars each. The rest are smaller, sometimes much smaller. Some contain only a few 100 million stars. Some contain only a few million, and we continue to discover new ones. As recently as a few years ago, astronomers found previously unknown dwarf galaxies orbiting the Milky Way. These are our immediate neighbors, closer than most galaxies we study, and yet we are still finding new ones because they are so faint that they escape detection in earlier surveys. If we are still discovering galaxies this close to home, imagine how many we are missing at greater distances. A dwarf galaxy that is easy to see from a few million light-years away becomes extremely difficult to detect at 100 million light-years. At 1 billion light-years, it is essentially invisible to most telescopes. At 10 billion light-years, even the most powerful instruments would struggle to find it. This means that our census of distant galaxies is heavily biased toward large, bright galaxies. The giants are easy to spot. The dwarfs remain hidden. If the ratio we observe in the local group holds across the universe, and theory suggests it should, then the vast majority of the 2 trillion galaxies are small dwarf galaxies. Perhaps 70 or 80% of all galaxies fall into this category. But our observations are dominated by the 20 or 30% that are large and bright. The unseen universe is teeming with dwarf galaxies, populations of small stellar systems that we know must exist, but which we cannot observe directly at cosmological distances. Galaxies without substance. There is a class of galaxies so diffuse, so spread out, that they are almost ghostly. These are called ultra-diffuse galaxies, and they represent another major component of the unseen universe. An ultra-diffuse galaxy might have a size comparable to the Milky Way, spanning tens of thousands of light years, but it contains far fewer stars. Instead of hundreds of billions of stars packed into that volume, an ultra-diffuse galaxy might have only a few 100 million or a few billion stars scattered thinly through space. This gives them an extremely low surface brightness. If you think of brightness per unit area, these galaxies are among the faintest objects in the universe. Imagine two light bulbs, both producing the same total amount of light. But one is concentrated in a small space, while the other is spread out over a large area. From a distance, the concentrated bulb is easy to see. The diffuse bulb is barely visible, fading into the background. Ultra-diffuse galaxies are like cosmic versions of that spread-out bulb. They emit plenty of light in total, but it is distributed so thinly that from any given direction, they appear extremely faint. These galaxies were largely unknown until about a decade ago. They were not part of the standard galaxy classifications because earlier surveys simply did not detect them. The techniques used to find galaxies were optimized for relatively compact, bright objects. Ultra-diffuse galaxies slipped through the cracks, too faint per unit area to trigger detection in automated surveys. When astronomers finally began looking specifically for low surface brightness objects, they found ultra-diffuse galaxies everywhere. Thousands have been identified so far, mostly in relatively nearby galaxy clusters where careful observations have been conducted. But these represent only the nearest, brightest examples. At greater distances, ultra-diffuse galaxies become essentially invisible. They fade into the background light of the sky, indistinguishable from noise. The unseen universe almost certainly contains billions of ultra-diffuse galaxies, possibly as many as 1 or 200 billion, a substantial fraction of the total galaxy population. They are there, occupying space, containing stars, participating in cosmic evolution. But they remain largely invisible to our current surveys. The stars between galaxies. Not all stars belong to galaxies. Some drift alone through the vast spaces between galaxies, orphaned by violent events, scattered into the cosmic wilderness. These are called intra-cluster stars or intergalactic stars, and they represent another invisible population. When galaxies collide, when two massive stellar cities merge together over hundreds of millions of years, the gravitational chaos can fling stars outward at high velocities. Some of these stars escape their parent galaxies entirely, ejected into the surrounding space. In galaxy clusters, where hundreds or thousands of galaxies are bound together by gravity, there can be enormous populations of these wandering stars. Observations of nearby galaxy clusters suggest that between 10 and 40% of the total starlight in a cluster comes from intergalactic stars rather than from galaxies themselves. This is a staggering number. It means that a substantial fraction of the stars in the universe are not bound to any galaxy. They drift in the dark spaces between, invisible to us not because they are intrinsically faint, but because they are not concentrated in recognizable structures. When we look at a galaxy cluster, we see the bright knots of light that are the individual galaxies. We do not see the faint, diffuse glow of intergalactic stars spread throughout the cluster, because that glow is too faint to detect except in the nearest clusters where very sensitive observations can be made. At greater distances, this population is completely invisible. We know it must exist based on theory and on observations of nearby clusters. but we cannot directly observe it in most of the universe. The unseen universe contains uncounted trillions of stars drifting between galaxies, expelled by ancient collisions, too scattered to form recognizable structures, too faint to detect individually. They are out there, shining in the darkness, invisible. The first lights let us journey backward, in time now, to the very beginning, to the epoch when the first galaxies were forming, when the universe was transitioning from darkness to light. The James Webb Space Telescope was designed specifically to study this era, and its observations have been remarkable. Webb has found galaxies from when the universe was only a few 100 million years old, revealing a cosmos already surprisingly rich in structure and star formation. But even Webb sees only the brightest galaxies from this era. The smallest, faintest primordial galaxies remain beyond its detection threshold. These tiny galaxies might have contained only a few million stars, but they played crucial roles in cosmic history. They were among the first objects to emit ultraviolet light capable of ionizing the hydrogen gas that filled space, transforming the universe from opaque to transparent in a process called ionization. Theoretical models suggest there should have been vast numbers of these small early galaxies, perhaps billions of them scattered across the young universe. They were the seeds, the building blocks that would later merge and grow into larger galaxies like the Milky Way. But most of them are invisible to us. They are too faint, too distant, too deeply redshifted for current instruments to detect. We see only the largest, brightest examples, the galaxies that were unusually massive for their time. The typical early galaxy, the common representative of that era, remains hidden. This matters because without understanding the full population of early galaxies, we cannot fully understand how the universe evolved from the smooth, nearly uniform state revealed by the cosmic microwave background to the structured, galaxy-filled cosmos we inhabit today. The unseen universe contains the complete story of cosmic dawn, the details of how light first conquered darkness, how stars first gathered into galaxies, how structure first emerged from simplicity. We are glimpsing fragments of that story with Webb and with other advanced telescopes, but most of the narrative remains hidden, waiting for future instruments sensitive enough to bring it into view. The hidden structures. The universe is not smooth. Matter is not distributed uniformly through space. Instead, galaxies are organized into structures called the cosmic web, a vast network of filaments and sheets and clusters with enormous voids in between. These filaments are like the threads of a vast, three-dimensional spider web stretching across hundreds of millions of light years. Where filaments intersect, you find galaxy clusters, dense concentrations of hundreds or thousands of galaxies bound together by gravity. Between the filaments are voids, regions that can be hundreds of millions of light years across and which contain very few galaxies. This cosmic web is the result of gravity acting on tiny density fluctuations that existed in the early universe. Regions that were slightly denser attracted more matter over time, growing into the filaments and clusters we see today. Regions that were slightly less dense lost matter to their surroundings and became voids. But here is the remarkable thing. We have mapped the cosmic web in only small regions of the universe. Our knowledge of large-scale structure is based on surveys that have observed millions of galaxies, which sounds impressive until you remember that there are 2 trillion galaxies in total. Most of the cosmic web remains unmapped. We have traced a few major filaments in our cosmic neighborhood. We have identified the largest nearby clusters and voids. But at greater distances, our maps become sparse, incomplete, showing only the brightest structures while missing the finer details. It is like trying to understand a spider web by looking at a few small patches. You see a strand here, a junction there, but you cannot perceive the overall pattern, the full three-dimensional architecture. The unseen universe contains the complete cosmic web, the full, large-scale structure that organizes matter across the observable universe. This structure exists. Theory predicts it. Simulations reproduce it. But actually observing it requires mapping millions of galaxies across enormous volumes of space. And we have only begun that task. The explosive universe. The universe is not peaceful. It is punctuated by violent events, by explosions and eruptions that release tremendous amounts of energy in brief spans of time. Stars explode as supernovae, destroying themselves in blasts that can briefly outshine entire galaxies. Gamma-ray bursts, the most energetic explosions known, release more energy in a few seconds than the sun will produce in its entire lifetime. Black holes tear apart stars that venture too close, creating bright flares that fade over weeks or months. These are called transient events because they are temporary, appearing suddenly and then fading away. They are happening constantly throughout the universe. At any given moment, thousands of stars are exploding in distant galaxies. Thousands of other cataclysmic events are unfolding, but we observe only a tiny fraction of them. Most occur in regions of sky we are not monitoring, or in galaxies too distant for us to detect the event, or at times when our telescopes are pointed elsewhere. Consider supernovae. A typical supernova in a distant galaxy might remain bright enough to detect for a few weeks. If your telescope happens to observe that particular galaxy during those few weeks, you will see the supernova. If you observe a week earlier or a month later, you will miss it entirely. To catch transient events, you need to survey large areas of the sky repeatedly, returning to the same regions frequently to spot changes. The Zwicky Transient Facility does this for the northern sky, scanning it every few nights and identifying thousands of supernovae and other changing objects. But ZTEF can only survey the relatively nearby universe. Transient events in distant galaxies are too faint for most surveys to detect. The unseen universe is filled with explosions we never observe. Every night, countless stars explode in galaxies billions of light years away. Most of these explosions go completely unnoticed. They occur, they fade, and they leave no record in human knowledge. They are part of the invisible cosmos, events that happen outside our field of view, beyond our detection threshold, contributing to the grand, ongoing drama of cosmic evolution, but remaining forever unobserved by us. The cosmic horizon. There is a fundamental limit to what we can see, a boundary beyond which the universe becomes permanently inaccessible. This is not a technological limitation that might be overcome with better telescopes. It is a feature of the universe itself, a consequence of cosmic expansion and the finite speed of light. The universe is approximately 13.8 billion years old. Light has been traveling since the Big Bang, but it has had only 13.8 billion years to reach us. This creates an observational horizon. Objects whose light has not yet had time to reach us are beyond this horizon. But the situation is more complex because the universe has been expanding while that light was traveling. When you account for expansion, the horizon is currently about 46.5 billion light-years away, making the observable universe about 93 billion light-years across. Beyond this horizon, there is more universe. Theory suggests it might be vastly larger, perhaps infinite. But we can never see it because light from those regions will never reach us. The expansion of space is carrying them away faster than light can travel. Not because they are moving through space faster than light, which would violate the laws of physics, but because space itself is expanding between us and them. This cosmic horizon is a permanent boundary. No amount of technological advancement will allow us to see beyond it. The unseen universe includes everything beyond the horizon, an entire realm that is fundamentally disconnected from us, causally separated, as inaccessible as if it existed in a different universe entirely. And the situation is getting worse. Dark energy is causing the expansion of the universe to accelerate. Galaxies that are currently just within our observable universe will eventually cross the horizon and disappear from view. In the distant future, billions of years from now, observers in the Milky Way will look out at a lonelier universe than we see today, with fewer galaxies visible, because many will have been carried beyond the cosmic horizon. The dark components. When we speak of the unseen universe, we must acknowledge that there are forms of invisibility deeper than simply not having observed something yet. The universe contains components that are fundamentally invisible, that do not emit light and cannot be detected directly by any telescope. Dark matter makes up approximately 27% of the universe's total energy density. It interacts with ordinary matter only through gravity. It does not emit, absorb, or reflect electromagnetic radiation of any kind. It is invisible to all our instruments. We know it exists because galaxies and galaxy clusters have more mass than we can account for with visible matter alone. The extra gravity must come from something, and that something is dark matter. But we cannot see it. We can only infer its presence from its gravitational effects. Dark energy is even more mysterious. It comprises about 68% of the universe's energy density. It is a force that causes the expansion of the universe to accelerate, pushing galaxies apart at an increasing rate. We do not know what dark energy is. We cannot detect it directly. We know it exists only because the universe is expanding faster than it should based on the matter we can account for. When you add these components together, roughly 95% of the universe is made of dark matter and dark energy, substances we cannot see and do not fully understand. Only about 5% is ordinary matter, the stuff that makes up stars and planets and us. And of that 5%, as we have discussed throughout this exploration, we have observed in detail only a tiny fraction. The visible universe, the matter that emits light and that we have actually studied, represents perhaps a few hundredths of 1% of the total universe. Everything else is invisible, either because it is dark matter and dark energy that fundamentally does not emit light, or because it is ordinary matter that we simply have not observed yet. The search for other worlds. The unseen universe has profound implications for one of humanity's deepest questions. Are we alone? If there are 2 trillion galaxies in the observable universe, and we have studied only 50 million of them in any detail, we have examined approximately 1/40,000th of the galactic population. Each galaxy contains billions of stars. Most stars have planets. Observations from missions like Kepler and TESS have confirmed that planetary systems are common, perhaps universal. Every star is a potential sun for a family of worlds. The number of planets in the observable universe is staggering, easily in the trillions of trillions. If even a tiny fraction of those planets are habitable, capable of supporting liquid water and stable conditions, and if life can arise on habitable planets, which seems plausible given that it arose on Earth, then the universe should be filled with life. But we have examined only the tiniest sample. We have studied a few thousand exoplanets in any detail. We have conducted searches for radio signals from nearby stars, but we have monitored only a small fraction of the sky for a limited time. The search for extraterrestrial intelligence is like trying to have a conversation with someone when you do not know their number, do not know what language they speak, and are listening to only one frequency out of billions of possible channels. The unseen universe almost certainly contains life. Statistically, it would be extraordinary if Earth were unique, but finding that life is incredibly difficult. The universe is vast. Signals would be faint. We do not know what to look for. Are civilizations communicating with radio, with lasers, with technologies we have not imagined? Every galaxy we fail to observe, every star system we do not study, every planet we do not characterize, might be home to life we will never discover. The unseen universe may be teeming with civilizations, with entire ecologies, with alien observers looking up at their own skies and wondering if anyone else is out there. They remain invisible to us, not because they do not exist, but because the cosmos is so large and our observations are so limited that the chances of our surveys intersecting with theirs are vanishingly small. The simulated cosmos, since we cannot observe most of the universe directly, astronomers use another tool to explore the unseen: computer simulations. These simulations are remarkable achievements, virtual universes created inside powerful computers, where the laws of physics are encoded and allowed to play out over billions of simulated years. A simulation begins with initial conditions based on observations of the cosmic microwave background, the oldest light in the universe. These observations show tiny density fluctuations in the early cosmos, regions slightly denser or less dense than average. The simulation takes these fluctuations and evolves them forward in time, using the laws of gravity, hydrodynamics, and star formation. Dark matter particles attract each other and clump together. Gas flows into the gravitational wells created by dark matter. Stars form, live, and die. Galaxies merge. Structures grow. After billions of computational hours, the simulation produces a virtual universe filled with galaxies. And remarkably, these simulated galaxies look very similar to the real ones we observe. They have realistic sizes, shapes, colors, and distributions. Projects like Illustris, Eagle, and the Millennium Simulation have created synthetic universes that closely match our observations of the real cosmos. This gives us confidence that the simulations are capturing the essential physics, that they are realistic representations of how the universe works. And the simulations make predictions. They predict that there should be approximately 2 trillion galaxies in the observable universe, matching the observational estimate. They predict vast populations of dwarf galaxies, low surface brightness galaxies, and other structures that we observe in limited numbers. The simulations are our best guide to the unseen universe. They tell us what should be out there, even if we have not observed it yet. When a simulation predicts billions of ultra-faint dwarf galaxies, and we have found only dozens, we can infer that the rest exist as predicted, but are too faint to detect with current instruments. The simulations allow us to extrapolate, to extend our knowledge beyond the boundaries of direct observation. But they are models, based on our current understanding of physics, which may be incomplete. They use approximations because we cannot simulate every detail. They are powerful but imperfect maps of the unseen. Tools that expand our vision but do not replace the need for actual observations. The future of observation. Let us turn our thoughts toward the future now, toward the telescopes and surveys that will push back the boundaries of the unseen universe in the coming decades. The Nancy Grace Roman Space Telescope is scheduled to launch in the late 2020s. Roman will have a field of view 100 times larger than Hubble's, allowing it to survey vast areas of sky relatively quickly. Its infrared sensitivity will enable it to detect faint distant galaxies, and its mission includes a high-latitude wide-area survey that will observe thousands of square degrees of sky, cataloging hundreds of millions of galaxies. This will be a major advance, moving from narrow pencil beam surveys to broad maps that reveal large-scale structure. On Earth, the Extremely Large Telescope is under construction in Chile. When completed, it will have a mirror 39 meters in diameter, making it the largest optical telescope ever built. The ELT will see fainter objects and resolve finer details than any existing telescope. It will study individual stars and distant galaxies, observe the atmospheres of exoplanets, and probe the early universe with unprecedented sensitivity. The square-kilometer array, being built across sites in Australia and South Africa, will be the most sensitive radio telescope ever constructed. SKA will map neutral hydrogen gas in galaxies, tracing the distribution of gas from which stars form. Hydrogen emits a characteristic radio signal, and by mapping this emission, SKA will reveal hidden reservoirs of gas, detect galaxies too faint to see at optical wavelengths, and study galaxy dynamics in new ways. These projects, along with others currently in development, will dramatically increase the number of galaxies we can observe. We might go from having studied 50 million galaxies to having studied hundreds of millions, or even a few billion. This would be genuine progress, a significant expansion of our knowledge. But even if we observe 1 billion galaxies, that is still only about 0.25% of the 2 trillion that exist. 99.5% would remain unseen. The fundamental constraint is time. There are only so many hours in a year, so many years in a human lifetime, so many decades in the operational lifetime of a telescope. We cannot observe everything. We must continue to make choices, to select which regions to study and which to leave for future generations. The pattern of discovery history teaches us that whenever we push into new observational territory, whenever we develop new capabilities or look at the universe in new ways, we find surprises. Quasars were unexpected when they were first discovered in the 1960s. These incredibly luminous objects, powered by supermassive black holes, did not fit into any existing framework. Gamma-ray bursts, discovered by military satellites in the 1970s, remained mysterious for decades before we understood they were the deaths of massive stars in distant galaxies. Dark matter was inferred in the 1930s and confirmed in the 1970s, revealing that most of the mass in the universe is invisible. Dark energy was discovered in the late 1990s when observations of distant supernovae showed that cosmic expansion is accelerating, implying the existence of a mysterious repulsive force filling all of space. Each of these discoveries came from observations that pushed beyond previous limits. They were not predicted by theory. They were stumbled upon, found by surprise when astronomers looked at the universe in new ways or with new sensitivity. This pattern suggests that the unseen universe likely contains phenomena we have not yet imagined. There are probably types of galaxies with properties unlike anything in our current catalogs. There may be structures on scales larger than we thought possible. There may be populations of objects we have not conceived of. The unseen universe is a reservoir of potential discoveries. We will not know what is there until we look. This is why exploratory surveys are so valuable. Observations that map large areas without targeting specific objects often yield the most surprising finds. The Sloan Digital Sky Survey, for example, was designed simply to map the sky systematically, to catalog galaxies without preconceived notions of what it would find. SDSS discovered quasars at higher redshifts than had been seen before. It revealed detailed structure in the cosmic web. It found unusual galaxies that did not fit existing categories. These discoveries came from looking systematically, from making the invisible visible without prejudice. The same will be true in the future. When Roman surveys billions of galaxies, it will undoubtedly reveal unexpected phenomena. When the Extremely Large Telescope studies distant galaxies in unprecedented detail, it will find things we did not predict. The unseen universe is not merely more of the same. It contains unknowns, and unknowns are the engine of scientific progress. The role of citizen science. Before we continue deeper into technical territory, let us pause and consider something important. The exploration of the universe is not solely the domain of professional astronomers working at major research institutions. There are ways for anyone to participate, to contribute to the revelation of the unseen universe. Projects like Galaxy Zoo invite people to help classify galaxies by examining images online. You do not need training or expertise. The website shows you an image of a galaxy and asks simple questions. Is it spiral or elliptical? Is it smooth or does it have visible structure? Your classifications are combined with those of thousands of other volunteers, and the aggregate results are used by researchers to understand galaxy populations. Galaxy Zoo has classified millions of galaxies, far more than professional astronomers could process alone. Volunteers have discovered unusual objects, including rare types of galaxies and unexpected structures. It is a genuine contribution to expanding human knowledge of the cosmos. Similar projects exist for other astronomical tasks. Planet Hunters asks people to examine data from exoplanet surveys, looking for the characteristic dips in starlight that indicate a planet passing in front of its star. Citizen scientists have discovered dozens of planets, some of which were missed by automated algorithms. There are projects for finding asteroids, identifying supernovae, mapping the moon, and more. These efforts demonstrate that the exploration of the universe is participatory. Anyone with curiosity and an internet connection can help. Every galaxy classified, every supernova spotted, every exoplanet candidate identified contributes to making the unseen universe a little less unseen. If this interests you, these projects welcome new volunteers. They provide training and support. You can contribute at your own pace, for as much or as little time as you choose. In doing so, you become part of the community working to expand human understanding of the cosmos. The limits of knowledge. There is a philosophical dimension to the unseen universe that is worth contemplating as we drift through these ideas together. What does it mean to live in a cosmos where most of what exists is beyond our ability to observe? How should we think about the limits of knowledge? For much of human history, the boundaries of the known world were practical and temporary. A mountain range was unexplored because no one had crossed it yet. An ocean was unmapped because no ship had sailed it. But these were solvable problems. Given time and resources, the mountain could be crossed, the ocean charted. The unseen universe is different in important ways. Some of it is practically unseen, not yet observed, but observable in principle. Given enough time and sufficiently powerful telescopes, we could see more galaxies, study more stars, find more planets. The boundary is technological and economic, not fundamental. But other parts are fundamentally inaccessible. The region beyond the cosmic horizon will never be visible no matter how long we wait or how advanced our technology becomes. The present state of distant galaxies is unknowable because the light showing their current condition will not reach us for billions of years, by which time they will have changed again. These are not temporary limits that might be overcome with clever engineering. They are built into the structure of space-time, into the nature of causality and information flow in an expanding universe. This should inspire humility. We are finite beings trying to understand an effectively infinite cosmos. We will never know everything. There will always be galaxies unobserved, questions unanswered, mysteries unsolved. The unseen universe is a permanent feature of our existence. A reminder that no matter how much we learn, the unknown remains vast. At the same time, this should not lead to despair or resignation. fact that we cannot know everything does not diminish the value of knowing something. Each galaxy we observe, each star we study, each planet we discover adds to the sum of human knowledge. We are building an understanding piece by piece, observation by observation, and the picture grows richer and more detailed with time, even if it can never be complete. The distribution of galaxy types. Let us return now to more concrete territory and explore specific types of galaxies that populate the unseen universe. Because understanding what we are missing requires understanding the diversity of galactic forms. Galaxies come in many varieties. The most familiar are the grand spirals, like the Milky Way and Andromeda, with their rotating disks and elegant spiral arms. Then there are elliptical galaxies, which are more rounded, ranging from nearly spherical to quite elongated. Ellipticals tend to contain older stars and have very little gas, so they form few new stars. There are also irregular galaxies that lack clear structure, often shaped by gravitational interactions or collisions. Within these broad categories are many subtypes. Spiral galaxies can be tightly wound or loosely wound. Some have prominent central bulges, others have small bulges or none at all. Some have bars, elongated structures of stars cutting across the center, while others are unbarred. Elliptical galaxies range from small and faint to massive giants containing trillions of stars. And there are intermediate forms, galaxies in transition, galaxies being transformed by mergers or other processes, but our observations are biased. We tend to see the largest, brightest examples of each type. A massive elliptical galaxy is easy to detect at great distances because it is intrinsically luminous. A small dwarf irregular is much harder to find. Yet dwarf galaxies outnumber giant galaxies by a large margin. In the local group, our immediate cosmic neighborhood, there are about 80 galaxies. The Milky Way and Andromeda are the two giants. Triangulum is a smaller spiral. The rest, more than 75 galaxies, are dwarfs. If this ratio holds across the universe, then perhaps 75 or 80% of all galaxies are dwarfs. But our distant surveys are dominated by observations of large galaxies. The invisible universe is disproportionately made up of small galaxies, the common citizens of the cosmic census that are too faint to detect at cosmological distances. These dwarfs are not unimportant. They are crucial for understanding galaxy formation. Large galaxies like the Milky Way grew by consuming smaller ones. The process of hierarchical merging, where small structures merge to form larger structures, is fundamental to cosmic evolution. Without understanding the dwarf population, we cannot fully understand how galaxies form and grow. The problem of cosmic variance. There is a subtlety in observational astronomy called cosmic variance, and it relates directly to the unseen universe. When we observe a small region of sky, we are looking at a particular part of the cosmos. But the universe is not perfectly uniform. Different regions have different properties. Some volumes of space might happen to contain more galaxies than average. Others might contain fewer. This is cosmic variance, the natural statistical fluctuation that comes from sampling a finite volume of an infinite or near-infinite universe. If we observe only a small region and try to draw conclusions about the universe as a whole, we might be misled. The region we observed might not be representative. It is like trying to understand Earth's climate by measuring the weather in a single city. If that city happens to be in a desert, you would conclude Earth is dry. If it is in a rainforest, you would conclude Earth is wet. Neither conclusion would be accurate. To get an unbiased view, you need to sample many different locations. The same is true for the universe. To understand the full diversity of galaxies and cosmic structures, we need to observe large volumes covering many different regions. But the deeper we look, seeking the faintest and most distant galaxies, the smaller the volume we can survey in detail. This creates a trade-off. We can look deep, seeing back to the early universe, but covering only a small area. Or we can look wide, mapping large regions, but not seeing as deeply. We cannot easily do both. This trade-off means that some of the unseen universe remains unseen not because we lack the technology, but because we have to choose between depth and breadth, and different scientific questions require different choices. Studies of the early universe need depth, long exposures of small fields to detect the faintest distant galaxies. Studies of large-scale structure need breadth, surveys that cover thousands of square degrees size to map the cosmic web. Both are necessary, but each leaves part of the universe unobserved. The galaxies and voids. The cosmic web, as we have discussed, consists of filaments and clusters with enormous voids in between. These voids are not completely empty. They contain galaxies, but far fewer than the denser regions. A typical void might be 200 million light-years across and contain only a few dozen large galaxies, where a similar volume in a filament or cluster might contain thousands. These void galaxies are scientifically interesting because they have evolved in unusual environments. Most galaxies experience interactions with neighbors, mergers, tidal forces, environmental effects from living in crowded regions. Void galaxies are isolated, evolving in near-perfect solitude. Studying them can reveal how galaxies develop when left alone without environmental influences. But finding void galaxies is difficult. By definition, they are in regions we do not often survey intensively. When astronomers map the universe, they naturally focus on the densest regions, the clusters and filaments where galaxies are abundant. Voids are often skipped or surveyed less thoroughly. Additionally, void galaxies tend to be smaller and fainter on average than galaxies in denser environments, making them harder to detect. The unseen universe includes vast numbers of lonely galaxies drifting through the voids. We know they must be there. Simulations predict them. Occasional deep surveys of void regions find them. But most remain unobserved, too faint and too far from the beaten path of astronomical surveys. They are cosmic hermits, isolated in the emptiest regions of space, largely invisible to our current observations. The merging universe. Galaxies do not evolve in isolation. They interact, collide, and merge. These interactions are transformative events that can completely reshape galaxies, and they are happening constantly across the universe. But observing mergers is challenging. When two galaxies merge, the process takes hundreds of millions of years. We cannot watch a merger happen in real time. We can only see snapshots, galaxies caught in various stages of interaction. Early in a merger, two galaxies might be distinct, but gravitationally disturbing each other, pulling out long tidal tails of stars. Later, they might be in close contact, their disks overlapping, with intense star formation occurring where gas clouds collide. Finally, they might coalesce into a single merged remnant, a new galaxy that looks nothing like either of the progenitors. Famous examples exist in the nearby universe. The antennae galaxies are two spirals in the process of merging, with spectacular tidal tails streaming away from the collision site. The mice galaxies, so named for their long, narrow tails, are another ongoing merger. Closer to home, the Andromeda Galaxy is approaching the Milky Way at about 110 kilometers per second. In roughly 4 to 5 billion years, The two will collide in a merger that will be spectacular, though any observers who witness it will see the event play out over millions of years as the galaxies make multiple close passes before finally settling into a single merged elliptical. But detecting mergers at large distances is difficult. The disturbances in galaxy structure are often subtle, requiring high-resolution images to see clearly. At distances of billions of light years, most mergers are invisible. We might see the galaxies, but we cannot resolve the fine details that would reveal they are interacting. This means the rate of mergers in the distant universe is uncertain. We can see some, the most obvious and dramatic ones, but we are missing the majority. The unseen universe contains countless ongoing mergers. Galaxies in the process of transformation, collisions that are reshaping the structure of the cosmos, but which occur beyond the resolution of our telescopes. The hidden reservoirs of gas galaxies are not just stars. They contain gas, the raw material from which future stars will form. This gas is mostly hydrogen, the simplest and most abundant element, and it exists in several forms. There is cold molecular hydrogen in dense clouds, the direct precursors to star formation. There is warm atomic hydrogen spread more diffusely through galactic disks. And there is hot ionized gas in galactic halos and in the spaces between galaxies. Much of this gas is invisible at optical wavelengths. It does not emit light we can see, but it can be detected at other wavelengths. Molecular hydrogen is typically traced using carbon monoxide, which emits radio waves. Atomic hydrogen emits a characteristic radioline at 21 centimeters. Hot ionized gas emits X-rays and can affect the cosmic microwave background through the Sunyaev-Zeldovich effect. But detecting gas in distant galaxies is even more challenging than detecting the stars. The signals are faint. Radio observations require large telescopes and long integration times. Many surveys focus on stars and simply do not have the capability to map gas effectively. The unseen universe includes enormous reservoirs of gas that we know must be present, but which we have not observed. Every galaxy contains gas. In star-forming galaxies, the gas might comprise 10 or 20% of the total baryonic mass. In young galaxies in the early universe, the gas fraction was even higher, perhaps 50% or more. But we have maps of gas for only a small fraction of known galaxies, mostly nearby ones where detailed observations are feasible. For the vast majority of distant galaxies, we know nothing about their gas content. We infer it from models and from observations of similar nearby galaxies. But direct observations are lacking. The Future Square Kilometer Array will help by mapping neutral hydrogen across large volumes of space. But even SKA will not observe all galaxies. Most will remain unmapped, their gas content unknown, part of the unseen universe. The census of black holes. At the center of most large galaxies, possibly all of them, there is a supermassive black hole. These objects contain millions or billions of times the mass of the Sun, compressed into a region smaller than our solar system. They are the engines that power quasars when gas falls into them. And they play important roles in regulating galaxy evolution by ejecting energy and material through jets and winds. But we do not have a complete census of supermassive black holes. We can detect them only when they are actively feeding, when gas is falling in and emitting intense radiation, or when we can observe stars orbiting very close to them and measure their gravitational influence. Most supermassive black holes are dormant. They sit quietly at the centers of their galaxies, not actively consuming gas, not emitting detectable radiation. They are invisible in the sense that we cannot see them directly. We infer their presence from theory. Galaxy formation models predict that supermassive black holes should be ubiquitous, and observations of nearby galaxies confirm this. But in distant galaxies, we usually cannot detect the black hole unless it is active. The unseen universe contains billions of supermassive black holes that we know must exist, but which remain unobserved because they are not currently producing detectable signals. Similarly, there are smaller black holes, the remnants of massive stars that exploded as supernovae. These stellar mass black holes are even harder to find. They are typically detected only when they are in binary systems with normal stars, pulling gas from their companions and emitting X-rays. Isolated black holes drifting alone through space are essentially invisible. Theory predicts there should be tens of millions of stellar mass black holes in the Milky Way alone, the accumulated remnants of billions of years of star formation and death. We have found only a few dozen, the ones that happen to be in detectable binary systems. The rest are part of the unseen universe, dark objects that neither emit nor reflect light, detectable only through gravitational effects if something happens to pass nearby. The relics of cosmic dawn. In the first few 100 million years after the Big Bang, the first stars formed. These were different from stars today. They formed from gas that was purely hydrogen and helium, with none of the heavier elements that later stars would inherit from previous generations. Because of their composition, these first stars, called population 3 stars, were likely very massive, perhaps hundreds of times the mass of the Sun. They lived fast and died young, exploding as supernovae after only a few million years and enriching the surrounding gas with the first heavy elements. We have never directly observed a population 3 star. They all died billions of years ago, and they were located in the very distant universe where they would be incredibly faint and difficult to detect even when they were alive. But the James Webb Space Telescope is searching for them, looking for their distinctive spectral signatures in the earliest galaxies. If Webb or future telescopes can find evidence of population 3 stars, it would be a major discovery, a window into the very first generation of stars in the universe. But even if Webb finds a few examples, most population 3 stars will remain part of the unseen universe, too faint and too distant to observe directly. We might infer their properties from the chemical composition of the next generation of stars, which inherited the elements they produced. But the stars themselves will remain invisible, relics of cosmic dawn that left no direct trace except the heavy elements they scattered into space. The present state of the distant universe. Here is a subtle but profound aspect of the unseen universe that deserves careful consideration. When we observe distant galaxies, we see them as they were in the past. A galaxy 10 billion light-years away appears as it was 10 billion years ago, when the light we are receiving left it and began its journey across space. That galaxy still exists. It is out there right now, somewhere in space. But it has continued to evolve. Stars have formed and died. The galaxy might have merged with others. Its structure might have changed completely. The present state of that galaxy is invisible to us because the light showing its current condition is still traveling through space and will not reach Earth for another 10 billion years. In a sense, the unseen universe includes not just galaxies we have not observed, but also the present states of galaxies we have observed. We have seen their past. Their present remains hidden, waiting billions of years in the future to become visible. This creates an interesting philosophical point. Our maps of the universe are not maps of the universe as it is now. They are maps of the universe across time, showing different objects at different epochs, all superimposed into a single view. It is a temporal composite, not a snapshot of any single moment. The true present state of the universe, what every galaxy looks like right now at this instant, is fundamentally unknowable to us because information takes time to travel and the cosmos is so vast that light from distant regions is always showing us the past. The cosmic microwave background. Among all the things we can observe, there is one component of the universe we have mapped almost completely: the cosmic microwave background. This is the oldest light in the universe. Radiation that was emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely. The cosmic microwave background fills all of space, coming from every direction, and it has been mapped with exquisite precision by satellites like COBE, WMAP, and Planck. These missions measured the temperature of the microwave background across the entire sky, revealing tiny fluctuations, variations of only a few parts in 100,000. Those tiny fluctuations are the seeds from which all structure in the universe grew. Regions that were slightly denser became the sites where galaxies and clusters would later form. The cosmic microwave background is one of the few things we have observed completely. We have mapped the entire sky in microwave light. But this is the universe at 380,000 years old. It shows us the infant cosmos, smooth and simple, before any stars or galaxies existed. The universe today, at 13.8 billion years old, is vastly more complex. All the galaxies, all the structure, all the richness we see today grew from those tiny seeds visible in the microwave background. The unseen universe is everything that developed from those seeds, but which we have not yet observed. It is the difference between seeing the seeds and seeing the mature forest that grows from them. We have mapped the seeds completely through the microwave background. We are still in the early stages of mapping the forest. The role of dark matter. We cannot discuss the unseen universe without acknowledging the role of dark matter. Because dark matter is the scaffolding upon which visible structures are built. Dark matter does not emit, absorb, or reflect light. It is invisible to all electromagnetic radiation. We know it exists only through its gravitational effects, through the way it influences the motion of stars and galaxies, and through gravitational lensing. In the early universe, dark matter began to clump under gravity before ordinary matter did. Because dark matter does not interact with radiation and so is not held back by pressure. Dark matter formed the first structures, gravitational wells into which ordinary matter later fell. When hydrogen and helium gas flowed into these dark matter halos, it compressed, heated, and eventually formed stars. Galaxies formed at the locations where dark matter had already created deep gravitational potentials. The visible galaxies we see are only the luminous centers of much larger dark matter halos. The Milky Way, for example, is surrounded by a halo of dark matter that extends far beyond the visible disk, containing perhaps 10 times more mass than all the stars and gas combined. We cannot see this halo directly, but we can infer its presence from the way it affects the orbits of stars and satellite galaxies. The unseen universe includes all this dark matter, a vast web of invisible substance that outweighs visible matter by a factor of 5 or 6. When we map galaxies, we are mapping only the bright cores of much larger dark matter structures. The full distribution of matter in the universe, most of which is dark, remains largely unseen. The acceleration of everything. The expansion of the universe is accelerating. This was discovered in the late 1990s through observations of distant supernovae, and it implies the existence of dark energy, a mysterious force that fills space and pushes everything apart. Dark energy makes up about 68% of the universe's total energy density, far more than dark matter or ordinary matter. It is driving the acceleration, causing galaxies to recede from each other at ever-increasing rates. This acceleration has profound implications for the unseen universe. Galaxies that are currently just within our observable universe are being carried away. Their recession velocity, the speed at which they are moving away from us due to cosmic expansion, is increasing. Eventually, their recession will exceed the speed of light. Not because they are moving through space faster than light, but because space itself is expanding between us and them. When this happens, those galaxies will cross the cosmic horizon. Their light will never reach us again. They will become part of the permanently unseen universe, carried beyond the boundary from which light can travel to Earth. This is already happening. Galaxies at the edge of our observable universe are on the verge of disappearing. In the future, more and more galaxies will cross the horizon as the acceleration continues. Billions of years from now, the observable universe will be smaller than it is today, containing fewer galaxies because many will have been carried beyond reach. Future astronomers, if they exist, will look out at a lonelier cosmos, with only the nearest galaxy groups remaining visible. Everything else will have disappeared beyond the horizon, part of an unseen universe that is growing as the cosmos ages and the acceleration intensifies. The challenge of faintness. Let us return to the practical challenges of observation and consider the problem of faintness in more detail. When we say a galaxy is faint, we mean that very few photons from that galaxy reach Earth per unit time. A nearby bright galaxy might send billions of photons per second toward Earth. At our location, some of those photons enter a telescope, creating a strong signal. A distant faint galaxy might send only a few photons per second. Across the entire collecting area of a large telescope, you might capture only a handful of photons from that galaxy each second. And those photons must be distinguished from background noise, light pollution, air glow, scattered moonlight, cosmic rays, thermal noise from the detector. The signal from the galaxy might be only slightly brighter than the noise. To reliably detect such a faint object, you need to collect photons for a long time, accumulating signal until it is clearly above the noise threshold. This is why deep surveys require such long exposure times. The Hubble Ultra Deep Field accumulated about 11.5 days of total exposure time. Hubble observed the same small patch of sky repeatedly over many months, taking exposures during each orbit, and then all those exposures were combined into a single deep image. The result revealed galaxies so faint that they represented only a tiny handful of photons above the background. Without those long exposures, those galaxies would have been invisible, lost in the noise. Now imagine doing this for the entire sky. There are millions of patches like the ultra-deep field. If each requires 11 days of exposure, you need millions of 11-day observing campaigns. Even if you had 100 telescopes working simultaneously, it would take thousands of years. This is the fundamental barrier. Faint objects require long exposures. The sky is large. There are not enough telescopes or enough time to observe everything deeply. Selection bias. Every astronomical survey has selection biases, systematic effects that make some types of objects easier to find than others. These biases mean that the galaxies we have observed are not a representative sample. They are skewed towards certain types. Bright galaxies are easier to find than faint ones, so surveys are biased toward luminous objects. Large galaxies are easier to resolve than small ones, so surveys favor big objects. Galaxies with certain colors stand out more, creating color biases. Regions of sky that are easily accessible from major observatories get observed more often. creating spatial biases. All of these effects mean that when we look at our catalogs of observed galaxies, we are not seeing a random sample of the universe. We are seeing a biased subset. Understanding these biases is crucial for interpreting observations. If we want to estimate the total number of galaxies, we cannot simply count the ones we have observed and assume that is the total. We must correct for the fact that we are missing large populations of faint, small, distant, or otherwise hard-to-detect galaxies. Astronomers use statistical methods to make these corrections. They model the selection function of a survey, the probability of detecting a galaxy as a function of its properties. By understanding what the survey is good at finding and what it misses, they can estimate the true underlying population. This is how we arrive at the estimate of 2 trillion galaxies, even though we have observed only 50 million. The estimate includes statistical corrections for all the galaxies we know we are missing. But these corrections have uncertainties. The true number could be different. We will not know for certain until we observe a much larger fraction of the universe. The morphology of the invisible. When we think about the unseen universe, it is useful to categorize the different types of invisibility, to understand the various reasons why things remain unobserved. Some galaxies are invisible because they are too faint. They emit light. But by the time that light reaches Earth, it is too dim to detect with current instruments. These galaxies could be observed in principle if we had more sensitive telescopes or longer exposure times. Their invisibility is technological and temporary. Some galaxies are invisible because they are behind dust, either dust in our own Milky Way or dust in other galaxies between us and them. These galaxies could be observed if we use different wavelengths, like infrared or radio, that penetrate dust more effectively. Their invisibility is wavelength dependent. Some objects are invisible because they do not emit light, like dark matter and dormant black holes. These could never be observed directly with telescopes, but they might be detected through their gravitational effects. Their invisibility is fundamental to their nature. Some regions are invisible because they are beyond the cosmic horizon, carried away by cosmic expansion faster than light can travel. These are fundamentally inaccessible, and their invisibility is permanent, a feature of the structure of space-time. And some things are invisible simply because we have not looked yet. The sky is vast, and we have not pointed our telescopes everywhere. These are invisible only temporarily, waiting for future surveys to bring them into view. The unseen universe is a mosaic of all these forms of invisibility, each requiring different approaches to reveal what lies hidden. The contribution of gravitational lensing. There is a technique that allows us to see farther and fainter than would otherwise be possible. Gravitational lensing. This phenomenon occurs when a massive object, like a galaxy cluster, sits between us and a more distant galaxy. The cluster's gravity bends the path of light from the distant galaxy, acting like a natural telescope that magnifies the background object. In some cases, the magnification can be dramatic, making a galaxy appear 10 or even 100 times brighter than it would otherwise. This brings it within the detection threshold of our telescopes, revealing objects that would be part of the unseen universe without the lensing magnification. The Hubble Frontier Fields program used this technique, observing 6 massive galaxy clusters in extreme detail and studying the lensed background galaxies revealed around them. Hundreds of faint distant galaxies were found through lensing, objects that would have been invisible in direct observations. But lensing is rare. The geometry must be just right, with a massive cluster positioned odd between us and a background galaxy. Most distant galaxies are not lensed. They remain invisible, too faint to detect without the boost provided by lensing. Astronomers are conducting systematic searches for lensed galaxies, scanning the regions around known massive clusters. But this can only reveal a small fraction of the total population. For every lensed galaxy we find, there are thousands of similar unlensed galaxies at the same distance that we cannot see. Lensing pulls a few objects out of the unseen universe, offering glimpses into realms that would otherwise be inaccessible. But it cannot reveal everything. Most of the faint, distant universe remains hidden. The cosmic web in detail. The cosmic web is one of the most striking features of large-scale structure, a network of filaments and nodes that organizes matter across the universe. Galaxies are not scattered randomly. They lie along these filaments, like cities along highways, with dense clusters at the intersections and vast voids in between. But our maps of the cosmic web are incomplete. We have traced it in relatively nearby regions where we have observed enough galaxies to see the pattern. At greater distances, our maps become sparse. We see hints of structure, suggestions of filaments, but we do not have enough data points to trace the full network. It is like trying to see a spider web in fog. You catch glimpses of individual strands, but you cannot perceive the complete architecture. The unseen universe contains the full extent of the cosmic web, the complete three-dimensional structure spanning billions of light years. Computer simulations predict what it should look like, and these simulations show intricate networks with hierarchical structure on all scales. But actually observing it requires mapping millions of galaxies across enormous volumes, and we have only begun that task. Future surveys like those planned for the Roman Space Telescope will help. But even these will not map everything. Much of the cosmic web will remain invisible, inferred from simulations and from the limited observations we have, but not directly traced in its full complexity. The impact on cosmology. The unseen universe has direct implications for cosmology, the study of the universe as a whole. Our understanding of cosmic history, of how the universe formed and evolved, is based on observations. But if we have observed only a tiny fraction of what exists, how confident can we be in our cosmological models? The answer is that our models are based on statistical samples, not complete censuses. We do not need to observe every galaxy to understand galaxy formation. We need to observe representative samples, enough galaxies of different types at different distances to piece together an evolutionary sequence. Similarly, we do not need to map every bit of structure in the cosmic web to understand how structure forms. We need enough observations to test our theories, to see whether the predictions of simulations match reality. And in many ways, they do. The galaxies we have, the galaxies observed match the properties predicted by simulations. The large-scale structure we have mapped looks like what theory predicts. This gives us confidence that our models are on the right track, but there are uncertainties. Because we have not observed everything, there is always the possibility that we are missing something important, some population of objects or some type of structure that would change our understanding if we knew about it. This has happened before. Dark matter was discovered because galaxy motions did not match expectations. Dark energy was discovered because the expansion rate did not match predictions. Both required us to revise our cosmological models fundamentally. The unseen universe might contain other surprises, other components or phenomena that we have not detected yet, but which would alter our understanding if we found them. This is why continuing to push the boundaries of observation is important. Every new survey, every new telescope, every increase in sensitivity gives us a better sample and reduces the chances that we are missing something crucial, the loneliness of scale. There is an emotional dimension to the unseen universe that is worth acknowledging as we drift through these thoughts together. The scale of what we are discussing is almost incomprehensible. 2 trillion galaxies, each containing billions of stars, most of them unseen and unstudied. Trillions of planets. Countless worlds where conditions might allow life to arise. And we have examined only the tiniest fraction. The numbers are so large, they become abstract, losing their power to move us. But sometimes it helps to make it personal, to connect these vast abstractions to human experience. Think about this. You are made of atoms forged inside stars. The carbon in your cells, the oxygen you breathe, the iron in your blood. All of it was created in stellar furnaces billions of years ago, then scattered into space when those stars died. You are literally made of stardust, connected materially to the cosmos in the most direct way possible. And yet, most of the cosmos remains unseen. Most of the stars whose deaths might have contributed atoms to your body will never be identified. Most of the galaxies that contain worlds similar to Earth will never be observed. Most of the potential life in the universe will never be contacted. We are surrounded by a vastness that we can barely perceive, living in a tiny bubble of observed space within an effectively infinite cosmos. This should inspire both humility and wonder. Humility because we are so small, because our knowledge is so limited, because most of what exists is beyond our reach. Wonder because the universe is so much larger and richer than our everyday experience suggests, because there is so much left to discover, because the frontier stretches endlessly before us. The optimism of exploration. But let us not end on a note of loneliness or limitation. Let us instead embrace the optimism inherent in exploration. The unseen universe is not a barrier. It is an invitation. It reminds us that there is always more to learn, always new discoveries waiting, always another question to ask. Every generation of astronomers pushes a little farther, sees a little more deeply, reveals another piece of the cosmic puzzle. We have gone from not knowing that other galaxies existed to cataloging 50 million of them. We have gone from seeing the universe as static to understanding it as dynamic and expanding. We have discovered dark matter and dark energy, exoplanets and gravitational waves, quasars and gamma-ray bursts. Each discovery has expanded our vision, and each has revealed new mysteries. The unseen universe ensures that this process will continue. There will always be more galaxies to observe, more stars to study, more planets to discover. Future generations will build more powerful telescopes, develop more sensitive instruments, and push into regions we cannot currently reach. They will make discoveries we cannot predict, find phenomena we have not imagined, and expand human knowledge in ways we cannot foresee. This is the beauty of the unseen universe. It guarantees that science will never be finished, that exploration will never end, that there will always be frontiers to cross. We are not living at the end of discovery, running out of things to find. We are living at the beginning, having barely started to explore the cosmos. The unseen universe is vast beyond comprehension, but it is not unreachable. It is waiting, filled with wonders, ready to reveal its secrets to those curious enough to look. The gentle return. And so we come to the end of our journey together, this exploration of the universe we have never observed. The vast cosmic realm that remains hidden beyond our current view. We have traveled through many ideas tonight, drifting gently from the limitations of human vision to the edge of the cosmic horizon, considering the many ways that galaxies and stars and structures remain invisible. We have contemplated the practical barriers of technology and time, the fundamental limits imposed by cosmic expansion and the speed of light, and the philosophical implications of living in a universe where most of what exists is beyond our ability to see. Take a moment now to let these ideas settle. Feel the weight of the numbers, the vastness of the unseen. 2 trillion galaxies, only 50 million observed. 40,000 unseen for every one we have studied. And yet this is not cause for despair. It is cause for wonder. The universe is larger and richer than we can fully know, and that is a gift. It means there is always more to discover, always another mystery waiting, always another horizon to reach for. As you drift toward sleep, let your mind wander among the invisible galaxies, the ones we have never seen, the ones whose light is passing by Earth right now, unnoticed, carrying information about distant worlds and ancient times. Imagine them out there, 2 trillion cities of stars, each one a cosmos unto itself, most of them unknown, unseen, waiting for future generations to bring them into view. You are connected to this vast, unseen universe, made of the same atoms, governed by the same laws, part of the same story. And tomorrow, astronomers will continue their work, slowly and patiently revealing a little more of what lies hidden. One galaxy at a time, one observation at a time, expanding the boundaries of the knownness and pushing back the frontiers of the unseen. This work will continue for generations, perhaps for as long as human civilization endures, and it will never be complete. But that is as it should be. The journey is what matters, not the destination. The universe offers endless exploration, endless mystery, endless wonder. And now, let go of these thoughts. Let them fade like stars at dawn. Feel your breathing slow, your body relax, your mind grow quiet. There is nothing you need to do, nowhere you need to be. The universe will still be there tomorrow, vast and mysterious and waiting. And you will wake refreshed, ready to face a new day, carrying with you the knowledge that we are surrounded by wonders, that most of what exists remains unseen, and that this hidden cosmos is waiting, patient and eternal, for curious minds to reveal its secrets. Sleep well, traveler. Rest in the knowledge that you have glimpsed the edges of the infinite, that you have considered the vastness of the unseen, and that the universe, in all its mystery and grandeur, will be here when you wake, unchanged and enduring. Good night.